We've talked earlier about the gravitational field. Now that we've gone through electric charges and forces, we're going to discuss the electric field. The electric field starts with Coulomb's law, where the electrical force between two charges is K times the absolute value of each charge divided by the distance between them. Similar to the gravitational force, no contact is needed between the two charges for them to feel a force from the other charge. This action at a distance, which troubled so many people, is best understood by assuming that each charge has a field surrounding it, and this field affects all other charges that move through it. We call this the electric field. Find the electric field due to one charge. We're going to modify the notation in Coulomb's law just a little bit. We're going to assume that one charge is very, very, very big, and the other charge is a small, tiny positive test charge. I'm not quite sure why they call it a test charge, but that's pretty common. But it's so tiny, it doesn't really affect the bigger charge. It will have a negligible electric field due to its size. Now, we haven't really discussed electric field that much yet, but this guy is not going to do much. All of the electric field that we're interested in is generated by this large charge. We're also going to replace the R sub 1, 2 just with R. So here's the magnitude of the force. It's K times the absolute value of the large charge, the absolute value of the little tiny charge, divided by R squared. We're going to remove the absolute value signs here on the charges, and we're going to consider force as a vector. You can see the arrow that we put up there. It means this is the vector. And we're going to introduce a new term, R hat. Yep, that's what looks like a hat, so we're going to call it a hat. R hat is a unit vector. It is a magnitude of 1, hence the term unit, and it's a vector, and it points in the same direction as the force vector in this case. We're now going to divide both sides of Coulomb's law by little q, and we will define the result, the electric field, at that point in space. That point in space is a distance r from this large charge, and this tells you the direction it's at, r hat. And remember, the magnitude of this is 1. So the electric field is defined as kq divided by r squared. The charge, big Q, creates the electric field. It is a property of the space surrounding Q. The size of charge Q and the distance to a point determine the strength of the electric field at that point. The electric field is measured in newtons per coulomb, right? Force over charge, newtons per coulomb. In order to visualize this property of space, we're going to use something called electric field lines. They're mathematical abstractions that let us see what the strength of the charge is that generates the field and the force that it will exert on other charges that enter the field. Because if you multiply the strength of the electric field at any point by a charge that you put there, it gives you the magnitude of the force on the charge, right? Because we defined electric field as the force between two objects over Q. So if I now take a Q, not a test charge Q, but a substantial Q, I find that the force on Q at that point in space surrounding the charge that generated the electric field is going to be Q times E. The direction of the field gives you the direction of the force on a positive charge, right? So if the electric field is in this direction, and I put a positive charge here within the field, it's going to move that way. If I put a negative charge in this field, it will move in the opposite direction. There are 4 rules to help us draw these fields on a piece of paper. Electric field lines always begin on a positive charge and end on a negative charge. The density of the electric field lines distribution is proportional to the size of the charges. So if I wanted to show the electric field due to a positive charge here, it starts on a positive charge and goes out like that. These lines should all be the same size, but that's close enough. If I have a bigger charge, I will have more electric field lines. Now remember, these are just abstractions of what is really there. So I would look at this picture and know that this is a much stronger charge. Now the lines never cross, or else there would be multiple values of electric force at the intersection point. So what does that mean? So here's a charge, and let's say there's one field line, and then I do cross the field lines. So let's see what happens. If I were to put a positive charge here, if I use this electric field line, that would tell me it's going to accelerate in that direction. But if I use this electric field line, it tells me it goes in this direction. It can't go two ways, okay? So whenever you see lines crossing like that, somebody drew it badly. And the lines are continuous. You don't have an electric field going like this and then breaking apart and starting again. It has to go all the way through. If there is an isolated positive charge right here, it will create an electric field. You can see the lines going out radially from it. And any positive charge you put in this field will be repelled by this charge that is generating the electric field. So if I put a small positive test charge here, or even a bigger one, the field lines tell it it will accelerate in that direction. That's the direction of the force on this particle. And you can also see this follows one of our rules from the previous slide. Electric field lines originate on a positive charge. The charge, our positive charge here, is generating a spherically symmetric field, and it is proportional to 1 over r squared. The further away you get, the weaker the field is. But at any distance, if r is the same, it will feel the same strength of the electric field. Since r can point in any direction, we get the field line centered on the charge, and it's actually generating a sphere. Remember, a charge exists in three-dimensional space. This slide here is only in 2 dimensions, so we're representing it like this. It would really kind of look like a hedgehog, right, with spikes coming every different way, but it'd be very symmetric. If there is an isolated negative charge, it will create an electric field that looks very similar to the positive charge, except you can see that the arrows move this way. They point towards a charge. That means if I take any other positive charge, it will follow the direction of those field lines, and you see how it would be attracted to a negative. So the field lines give you the direction that a positive charge will move. If I had a negative charge here, that would move opposite the direction of the field line, so it would move that way, which makes sense because like charges repel. The definition of the electric field showed that the strength of the field, and actually the force, decreases as 1 over r squared. There's a way of visualizing it by looking at this picture here, by their density. Note that the electric field lines are closer together, more dense, when they're nearer the charge. For example, if I took a little, let's just draw a little shape like this. How many electric field lines are going through it? 1, 2, 3, 4. If I draw that same shape, well, it's going to be almost impossible, but I'll draw the same size shape. Looks like kind of a hot dog that's cooking. I have 1, maybe 2 lines going through it. So out here the field is weaker, in here the field is stronger. If you want to try this, there's a fantastic simulation from PHET from the University of Colorado. Please click on this and it'll enable you to create your own electric fields and with multiple charges. Michael Faraday created the concept of the electric field. He was born in London to a very poor family in 1791. At age 13, he apprenticed as a bookseller and binder while also attending local lectures on philosophical and scientific topics. So he was out of any formal schooling at that point, and as a matter of fact, his mathematics level was quite low. However, a member of the Royal Institute, recognizing some talent in Faraday, took notice of him and brought him several tickets to several Royal Institute lectures. In 1813, he was then invited to work at the Royal Institute, where he made unbelievable contributions to both physics and chemistry. The whole concept of field theory originated with Michael Faraday and is then used even today with quantum field theory. Albert Einstein had a few pictures on his office wall. One of them was Newton, one of them was James Maxwell, who we'll be talking about later in the course, and the other was Michael Faraday.